Hello and welcome to this lecture. So in this lecture, we'll start moving towards computing derivative for x bar a, where a is a general real number. Okay. So far we know how to compute this when a equals 0, right? What happens when a is 0? X power 0 is like big convention, it's 1. So x power 0 is 1, 1 is a constant, I know its derivative. If a equals 1, then I get just x, and x is identity function, I know its derivative, it's 1, right? But all other values of a, at this point at least, we don't seem to know the derivative, though for x squared we computed, right? You remember, for x squared we computed the derivative when that was 2x, okay? So let's see how I can slowly and steadily go towards x power a's derivative for any a that's real, using just the differentiation rules and some logic and all that, okay? So that's what I'm going to do in this lecture, okay? So let's begin with some simple. Once again, we'll go step by step by step. So slowly build easy cases, easy cases, easy cases, and go on. So you see the mathematical method always works like that. You know, you start with some very simple definitions and then use it in simple cases and more complicated, make some rules, make some logic around how the operation works, etc., etc. So this is the same method we'll use over and over and over again. I hope by now you're starting to appreciate this method as well. Okay. So derivative of x bar n when n is 1, 2, 3, 4, etc. Just integer, right? Positive integers, okay? So I know for n equals 1, I already know what the answer is, right? X prime equals 1. What can I do for x squared? Here is what I can do for x squared. What is x squared? X squared derivative is actually the same as x times x derivative. So here I can use the product rule, right? Notice this is just product of x and x. I know how to differentiate x. So I can use the product rule. It's x times the derivative of x plus the derivative of x times x. So what is this guy? This derivative is just 1. This derivative is just 1. X plus x, 2x. So notice, I mean, we also did this through directly from the limit definition, right? You remember, you can go back and check. We also got the 2x. Here is it may be presumably a simpler method, just using the product rule. Now what we did once from going from x to x squared, maybe we can fruitfully exploit it to go to x cubed also. How do you go to x cubed? X power 3 is x squared into x, isn't it? So if you take the derivative of x power 3, it's like taking the derivative of, it's exactly like taking the derivative of x squared times x whole derivative, right? Now we use the product rule here, and you already know what the derivative of x squared is. So this is x squared times x derivative plus x squared derivative times x, okay? Now what is x derivative? This is just 1. What is x squared derivative? It's 2x. 2x times x is 2x squared, totally you get 3x squared, okay? So for x power 3 prime, we are getting 3x squared. So now we start noticing a pattern. Notice this pattern. For x power 1, I just get 1. For x squared, it's like this 2 comes down and the exponent becomes 1 less, right? 2 times x. For x power 3 also, this 3 came down and multiplied, and the 3 became 2, 3 times x squared. So maybe there is a pattern here. So I'm going to make what is called an induction assumption. This is like a hypothesis. I'm just saying, hypothesis, I'm just guessing, okay? I'm going to guess based on this pattern that x power n derivative is n coming down and exponent reducing by 1, nx power n minus 1. Now notice this is an induction assumption. What is induction? It's like, I mean, this kind of thing is called induction. If you do integer after integer, you notice a pattern, and then you say for n, maybe that same pattern holds, okay? So this is called an induction assumption, and we do this induction assumption here. Now this induction is a very powerful method of proof, okay? You might have seen it in other math courses, but this is the first time we are seeing it in this class, so I'm just going a little bit more in detail. Now I made this assumption here. So how does induction work? Basically, you assume this is true, okay, and then try to ask, is the same true if I replace n with n plus 1, okay? So I've assumed up to n. Can I replace n with n plus 1, and will the same thing be true? If that is true, magically notice what happens. For n equals 1, it is true. For n equals 2, it is true. So, and for n, if it is true, then n plus 1 is true, okay? So I've logically now shown for all n, for any n, okay? So that's the magic of induction. Induction gives you a systematic method to verify a result for integer values of some variable. Okay, you check it for a few variables, find a pattern, make a guess for n, and see if that works for n plus 1 also. If it works for n and n plus 1 and works for a few initial cases, then by induction it works for everything. Like you start from there, next it works, next it works, next it works, like that it works for everything. Okay, so it's a wonderful way of proving things. So we're going to use induction here, right? X bar n prime is n x bar n minus 1. I'm assuming this at this point. Is it going to be true for n plus 1? And guess what? It's true. Okay, so that's called the next step verification. Okay, induction assumption always needs to follow, needs to be followed by next step verification for the proof to be complete. Okay, notice what's going on here. X power n plus 1 prime. What is x bar n plus 1? It's x bar n times x. So it's a product rule again. X bar n times x whole derivative. It's x bar n times the derivative of x plus x bar n derivative times x. Now notice this x bar n derivative, by the induction assumption, I know it is n times x bar n minus 1. If I put n times x bar n minus 1, I get n x bar n. Here there is an x bar n, so I get n plus 1 x power n. So what is true for n is also true for n plus 1. Okay, n plus 1 comes down and the exponent goes down by 1. So it was true for 2, it was true for 1, it was true for 2, and it's true for, if it is true for n, it's true for n plus 1. So true for 2, so it's true for 3, it's true for 4, it's true for 5, true for 6, so on, so on, so on, so on, so on, so on, forever. Okay, so by induction and next step verification, by induction, we have proved that x power n prime is n x power n minus 1. Okay, simple, isn't it? I mean, there are other ways of proving this. If you use more fancy results like some other way of bounding things and all that, you can do this. But this is a very, very elementary and simple method for proving derivative of x power n. Okay, but we want to show for x bar a for all a, right? N is just positive integers. How do you keep going further? We'll go further by using other rules. Okay, the next step is sort of very interesting. I'm going to push towards x power r by s, where r and s are positive integers. So basically this is rational numbers, positive rational numbers. All positive rational numbers are covered here, and x power a, where a is positive real. Okay, so let me start with this first, and then you will see by some limiting operation I can claim that this is true. Okay, so that's a slightly technical step, but this one we can prove very, very nicely using the composition rule. How do I use it? How do I use composition for this? So here is where the trick comes in. The function for which I need to find derivative is this guy, right? G of x is x power r by s. I don't know the derivative of this guy now. Okay. Now I'm going to compose it with a function f of x, which is x power s. Notice I've chosen this very smartly and correctly. Okay, x power s. What happens when I compose f with g, right? F with g. You put in g here, x power r by s, and then what is f? F simply raises anything it sees to the power s, right? That's what f does. Whatever you feed it, it's going to raise it to the power s. So instead of feeding x, I'm feeding it g of x, which is x power r by s, and it simply raises that to the power s to get x power r. Okay. What is wonderful about this is, I know how to differentiate x power r. So notice what I've done. My composition is done so that I get to a function which I know how to differentiate. R is just a positive integer. I can differentiate this. Now I can differentiate both sides of this guy. Okay. So notice these little tricks that we do. So these are the tricks that are slightly innovative in the mathematical method, right? So you have to use this next step of result, nothing very major, but you use this little bit of intuition to, sort of go towards. So you have an unknown problem. Can I do something to convert it into a known problem? Okay. And then sort of work with that and then get to the answer. Okay, so it's always that. Okay, so f of g of x is x bar r. Now I differentiate both sides. Use the composition rule here. Use the r x bar r minus 1 here, and you will see magically we'll get to the answer. So here is the idea. If I take f of g of x and its derivative, it's just r x bar r minus 1. How do I differentiate this? G of x raised to the power s, derivative is r times x bar r minus 1, and then this is just the composition rule, right? So it's f prime evaluated at g of x times g prime of x, isn't it? It is f prime evaluated at g of x. What is f prime? This also I know, no? Right? This is not any old function. This function also I can differentiate. It's also important. This f prime is s x power s minus 1. So s g of x power s minus 1. So f prime evaluated at g of x. That's what this guy is. And multiplied by g prime of x. That has to be equal to r x bar r minus 1. What is g of x now? It's x power r by s minus 1, power s minus 1 times g prime of x equals r times x bar r minus 1. Now from here to here is a very nice and simple algebraic verification. Okay, I'm going to leave it as an exercise to you. just take this x power to this side, s to this side, and do the computation here to show that this g prime of x is r by s, x raised to the power r by s minus 1. Okay. So, notice how we went from the unknown to known using this composition idea in this case, right. So, it is a slightly non-trivial idea to use, and what we are able to show wonderfully well is, even if the power is rational, right, if it is x power n, then we argued n comes down, then you get x power n minus 1. Even if the power is rational, r by s, the same thing happens, exact same thing happens. This r by s comes down entirely and x power r by s minus 1. Okay, the same type of formula is used for all positive rational numbers. Okay. Now, how do you go from rational numbers to real numbers? We know that, right? Real numbers are limits of rational numbers. So, since every real number, positive real number a is the limit of sequence of positive rationals, the same result is also true for a. Okay. So, it's a little bit technical. You have to sort of, if you want to make it, it can be made rigorous quite easily, not very hard, but you can write down all these things very carefully, actually come up with the limit of rationals, so that this goes to, that limit goes to a, and then argue why the definition for the derivative, the limit also can go in, and once the limit goes in, you will get this. Okay. So, that little rigorous technical part I am skipping. Okay. It's okay, in this class you can skip that, but you can see why, x power r by s derivative is this, like this, and a, even though a is some real number, a is very close to rational numbers, right. There is a sequence of rational numbers that come to a. So, for every rational number this is true, so for the real also it should be true. That is the sort of intuitive argument that I am making here. So, for any positive real number, x power a prime is ax power a minus 1. Okay. So, we are still not done. We have done for a positive real. Okay. So, that's a big step. But what about negative? Negative is not very hard. Okay. So, you will see the derivative of x power a real, for a positive, I know it is ax power a minus 1. So, for any real number a, it is ax power a minus 1. Okay. That I know. What do you do for negative? Okay. So, here again we will use the product rule in a very convenient way. What am I doing here? If a is less than 0, I am going to come up with a b such that x bar a times x bar b is 1. Okay, this is easy to do, right? B is minus a. Simply take minus a. So, x bar a times x bar b is 1 is possible. So, notice once again, I am just looking at another function which uses x bar a, but somehow it takes me to a known function, right? So, this is a very standard idea in mathematical deduction. When you take an unknown step and see if you can go towards the known, right? So, it's a very useful idea. So, once again, once I have this, I am going to take derivatives on both sides. If I take derivative on both sides, I will get 0 here, right? Derivative of 1 is 0, and then I use the product rule, x power a prime, x power b plus x power a times x power b prime is 0. Now, I know the derivative of x power b. Why? Because b is positive real. A is negative real, I don't know it, but b is positive real, I know it. So, you can do this a little bit. So, you see here x power a prime, b is minus a, right. So, x power minus a plus x power a times b x power b minus 1 is 0. Now, we do the algebra, put b equals minus a here, do the algebra, you will get x power a prime is again a x power a minus 1 if a is less than 0. Okay. So, finally after all this effort, we have the derivative of x power a for a real, any real number a, x power a derivative is a comes down, the exponent reduces by 1. Okay, a x power a minus 1. Okay, for any real number, this is true. Okay, I hope you enjoyed this little bit of lecture where we rigorously showed, we didn't lose too much rigor except for the very technical parts which in this kind of class it's not so important. We skipped that, but I sort of argued and showed you how, using the known facts that we have and the logic and deduction steps, we are able to show derivatives for more complicated functions. So, now this x power a is maybe not that complicated, but it's complicated enough, and it will give you, you'll see, you can now do derivatives for so many more functions using this. Okay, thank you.